Today we'll finish chapter 18. So what we've talked about are acids and bases, and we're going to finish talking just a couple topics on acids and bases, and then we're going to talk about what we call redox reactions, reduction and oxidation, so we can contrast the similarities and differences between the acid and base reactions and the redox reactions. Well, that's beautiful. Not sure why that popped up. So first, about acids. What does it mean if something's an acid? Jackie, can you not have the water there? Or is that, where is this?
Yeah, I forgot.
What is it that makes something an acid?
It donates.
Okay, acids donate, and what do they donate specifically? Protons or hydrogen ions. And what makes something a base then? It accepts them. So we're talking about ionic relationships where a proton leaves and becomes an ion. It leaves its electron behind. And we measure the pH. Oh man, I looked up what P stood for, and it was, oh man, I can't remember what it is. I looked it up because, we're talking about last class period. Now I've forgotten. But it's something of hydrogen, like proportion of hydrogen, something like that. The pH is what we use to measure if something is acidic or basic. And that pH equation was the pH is equal to minus the natural log of the concentration of hydronium ions. And so we saw that if I have water, just pure water, it will naturally have a concentration of 10 to the minus 7 moles per liter of hydronium. And likewise, 10 to the minus 7 moles per liter of hydroxide, the OH. And so the pH for water turns out to be 7. And we consider that, I circled blood by accident there. We consider water to be our neutral substance. So a pH of 7 is neutral. So something with a perfect pH of 7 is neither acidic nor basic, it's neutral. If the pH is not 7, it's going to be one or the other. As you can see there, if the pH is a number smaller than 7, that means it has a higher concentration of hydronium, and it is an acid. If the pH is a bigger number than 7, then it's a lower amount of hydronium, and it's a base. And so we see some typical substances. And we see, soft drinks, a pH of around 3. Around 3 is a pretty strong acid. So soft drinks are pretty strong acids. But we have other common things that are stronger. Vinegar is a slightly stronger acid than your soda, which means that you would have a better function of doing something like cleaning your toilet with vinegar than you would with soda. Right? Vinegar would be better with Coke. And what would be better than vinegar? Lemon juice. What would be better than that? Battery acid. That's for cleaning up only one thing. Somebody put a potential test question of what would be good for cleaning your sink. You have to be a little clear, because when you're using something like the Coca-Cola to clean your toilet bowl, what you're actually cleaning is you're having the acid attack things like lime deposits. And so you need the acid for that. For other things, something like the person had soap or detergent. Detergent would be better for cleaning away grimy type stuff. So it depends on what you're cleaning, what the best thing would be. So we do have to be a little clear on that. And I'm sure you know that you clean some things in your house with soap and ammonia that are bases, and some with vinegar and lemon juice that are acids. So it depends on what your point is, what you're trying to do, which works best. Of course, we don't consume that beverage, so I'm just going to cross it out. Those tomatoes are pretty acidic. So I don't know about you guys, but when I eat certain foods, foods I love, like pineapple, what happens when you eat a lot of pineapple? Yeah. Why is that?
Because it's acidic.
Because it's acidic, right. And the same would be true if I were to eat that much of tomato, but I just don't go to town on tomatoes like I do on pineapple, right? So these things that are highly acidic, they will irritate you if you get it on some of your more tender skin. I suppose if you were to have Coke just sitting here pooling on the sides of your mouth, that would probably also become tender. In case you cared, we have urine there is acidic. Now, that's a natural thing. There are people who religiously test their urine for its pH value because they have been convinced that if you make your body basic, as illustrated by your urine stream, then it's healthier for you. And your body, number one, is highly buffered. Your body works to keep your pH in a very, very small range. That blood is down here. What would you say about the acid or base level of blood? First, is it acid or base? And second, is it strong or weak? It's a weak base. It's a weak base. I believe it's around 7.35 plus or minus around 0.04 is the pH of blood. It doesn't have much variation. If it moves outside of that, you die. And so these people doing everything they can to make their body basic, you're just fighting your body that's trying to keep it at that, it's basic, but that weak base level. And sure, measuring your urine, you can change your urine's pH by what you eat, but it's, that whole testing your pH is kind of far-fetched. It's not something that most scientists would follow. You see seawater. Seawater is more basic. Oh, no. Baking soda. We're going to use baking soda for lab this week. The lab we're going to do is the one with the red cabbage stew. I don't remember the name of it. It's like page 189 or something. We're going to measure things if they're acidic or basic by putting them in our red cabbage stew. Hair remover. Sometimes I worry that I might be using that for shampoo, but that's your Drano stuff. It's a very strong base to dissolve the hair. And of course, oven cleaner is a very strong base. So oven cleaner, strong base. Things for cleaning your lime deposits, strong acids. Depends on what you want. But I just wanted you to see a range of substances and know that things we commonly use are all over that scale. We don't want to mess with anything that's above there, really. Right? Like battery acid. What happens if you get battery acid? Okay, you guys don't know this, do you? Get battery acid on your clothes? It dissolves them. Yay! Right? You don't want that. So reasons we don't want to mess with those. Hydrochloric acid, really, really strong acid. Use that as your reference. Notice it actually has a -1 pH. Right? So it doesn't stop at 0. What that means is it has more than 1 mole per liter.
Okay.
Right, which is certainly possible. The units aren't moles per moles or liters per liters. It's moles per liters. That's why it's possible. Okay, now how does this affect you as humans? You may or may not be familiar with the term acid rain. When I was your age, everybody was familiar with the term acid rain. So first and foremost, acid rain is actually naturally occurring. But that's because the atmosphere naturally contains carbon dioxide. And when we have water falling through that carbon dioxide, you create carbonic acid that gives water a pH that's somewhere in the ballpark of 5.5-ish. But with burning fossil fuels and coal, that releases a fair amount of sulfur-containing compounds into the atmosphere. And so that's what we worry about with acid rain. It's the sulfuric acid rather than the carbonic acid. So normal rain is acidic, but it's lightly acidic. But if you have that sulfur in the atmosphere, so you have the SO2, notice that looks just like HO. It doesn't look just like HO2. I was going to say H2O, but it's not the same as H2O. You have the sulfur dioxide combined with oxygen in the atmosphere. Of course, oxygen is a little over 20% of the atmosphere, so there's plenty of that. And it produces SO3, which then quickly reacts with water and rain to produce sulfuric acid. And that can make the pH a smaller value than 5, more acidic. And that's when we start to get worried. So by convention, if the pH of the rain is smaller than 5, it's called acid rain. Now, why would that be bad?
Doesn't it like hurt crops or something?
Okay, yes, it will hurt crops. It makes it hard for things to live if you have this acidic water. A second thing that is not really important, but is troubling nonetheless, is you have all these like marble monuments. Well, marble is just metamorphized. That means it's been heated and squished, so it's kind of changed its shape a little. Calcite, calcium carbonate. And that dissolves in acid. So you have these marble statues or marble tombstones or whatever, marble markers, and they dissolve in the acid rain. So they dissolve in water too, but they dissolve very, very slowly in water. But if you put them in a stronger acid, they dissolve quickly. That was the basis of one of the tests you did in the last lab. The lab where you put the material in acetic acid in vinegar. That was an acid, and that acid should make it undergo a chemical reaction that bubbled, right? And that's how we actually test. If you go out as a geologist, you always have just a little vial of acid, and you have a rock, and you're like, I wonder if that is calcite or if that's quartz. You drop a drop of that on the rock. That's what geologists do in the field to tell the difference. They put it on the rock, and if it bubbles, oh, that was calcite. If it doesn't bubble, oh, it must be quartz. So that's our acid rain. It looks like I have these backward because this is the thing that's always occurring. Why do we have carbon dioxide in the atmosphere? Good, Justin? Got nothing?
Our emissions.
Now, the textbook confused me, which I'm assuming means it confused you as well. It says that we have about 3,100 billion tons of CO2 in the air. Now, that's in the air of the entire Earth. And then it says most of that comes from natural sources like volcanoes and that kind of thing. But then it says man is contributing to that, so that man's contribution is 1.8 trillion tons. But it said most of it was natural. 18 is bigger than half of 31. That would be a majority. So that's where I was confused. How is more than half coming from man, and yet it says it's natural rather than man-made? At any rate, the amount of carbon dioxide in the atmosphere is higher than it normally would be because of humans. How do we produce carbon dioxide? Okay, one of them is through breathing. Yeah. I saw a meme on Facebook that said a certain political group would ban breathing if they could because it pollutes the atmosphere. A much bigger concern than humans breathing is going to be combustion. When we burn things, we often produce, water is the ideal thing that's coming out of burning, but we also produce things like carbon dioxide. And so with the Industrial Revolution, with a lot more burning of things for our plants and for our energy, so we have lights here, we're producing a lot more carbon dioxide gas that's going into the atmosphere. So that's, when we talk about global warming or climate change, the concern is primarily about, the concern you read about is primarily about that big jump in carbon dioxide caused by humans. So, here's an example of acid rain. What it does to a nice piece of calcium carbonate, and then over time dissolves so you can't read anything. And here, as we can see, the forest, it lived nicely in the acid rain. Not. So when that acid lands in water, especially in the oceans, tends to be basic when you have it in a natural environment. Because you have things like, I was trying to think of the actual chemicals in water, and suddenly I'm blank. But you have alkaline things like, sodium, potassium, magnesium, calcium in the water, which makes the water tend to be basic. And so the water acts as a buffer. It neutralizes the acid by having a reaction with the acid to make it so it's no longer in a form that can be acidic. And so you tend to buffer when you land in the water, but if you have too much acid, then you get an acidic pool, and you've got the extra hydroniums here. And then you see how much grows? Nothing. Nice, beautiful, non-leaved tree. And it's showing this rock stuff here. It's granite because it's leached away the limestone that was originally in the rock. What is limestone? It's calcium carbonate. So it's leached away the calcium carbonate. So this here was the limestone. You had the hydronium, the calcium carbonate produced water, carbon dioxide, and calcium ions. Ah, yes. The buffering of the ocean, typically a pH of 8.2. The ocean does something really important in terms of climate for us. We have this carbon dioxide in the atmosphere. When it comes into the water, it gets absorbed and it precipitates out that CaHCl3 as a rock. And so carbon gets encapsulated, the calcium and carbon get encapsulated as rock in the oceans. And so it helps to clear out the amount of carbon dioxide in the atmosphere, keeping it low. One theory on why Venus doesn't have any, Venus is super hot, has really thick clouds. One theory is that it never got cold enough for liquid water to form on its surface. And because it never had liquid water form on its surface, it never started cleaning out the carbon dioxide from the atmosphere and just was left with a runaway greenhouse effect. So the effects of the ocean absorbing carbon dioxide are important to us maintaining our ecosphere. But you've learned something about reaction rates. Reaction rates tend to go faster if it's hotter, right? You had concentration, temperature, and catalyst were the three things that would affect the rate of a reaction. And so with the water, we have that same thing, this reaction that is depositing rock in the ocean floor as it takes in carbon dioxide. It shifts toward producing carbon dioxide as the temperature goes up. So as the temperature goes up, the oceans release carbon dioxide. Temperature goes down, they absorb more carbon dioxide. So historically, when people are trying to determine paleo temperatures, how hot the Earth was in the past, they actually look at how much carbon dioxide was in the atmosphere. The more carbon dioxide, the higher the temperature of the Earth was. And it seems a little convoluted that now we're saying, okay, because of higher carbon dioxide, the Earth is warming, when in the past we said the Earth must be warming because of higher carbon dioxide, right? One, A caused B versus B caused A. And I am not a professional in the area. I can't do any analysis, but I assume that it is legit. Now switching to a different kind of reaction, what we call redox reactions. I know, it looks like red ox. The RED, the read part of redox, stands for reduction. And this is talking about electrons. So when we talked about acids and bases, we were talking about protons moving, right? Hydrogen nuclei, hydrogen ions. The redox is talking about gaining and losing electrons. And a simple rule, I've got it on the next slide. I was going to write it here. Losing and gaining electrons. When you lose an electron, it's oxidation. So this reaction here, 2 sodiums gives me 2 sodium ions plus 2 electrons. Doesn't seem like much of a reaction. There needs to be something else there to make that useful. That's what we would call a classic oxidation because the sodium lost electrons. So we have an abbreviation for this, or an acronym. That is right. LEO is the first one. Lose electrons, oxidation. So that's what LEO stands for. Lose electrons, oxidation. Then reduction is the opposite of oxidation. So, as Brittany Renee said, GER. Gain electrons, reduction. And so we have here an example, chlorine gaining 2 electrons. And of course, you put these two together and it makes sense. Right, so if I have, well, yeah, I'm not going to do that. But if you put those together, then you'd form an NaCl neutral thing. But that's what the difference is in a reduction and an oxidation. Now, oxidation tends to be exothermic. It gives off energy. And so when you burn something, it's an oxidation reaction. Anyone want to guess why they call it oxidation? Yeah, from what oxygen does to the reaction. Oxygen is a good oxidizing agent. It's something that's going to help you lose electrons. So, yes, here, Leo, GER, to our very famous Leo the Lion Says GER. And around these parts, Chuck Friedline wrote a famous song that I don't know. You can sing it?
No, I can't.
If I could, I would. All I know is Leo the Lion Says GER. That's all I know. Because when I was in high school, we didn't learn to sing it. We just learned Leo the Lion Says GER. What's the lion says? It's to help you remember the Leo and GER. Right? There's nothing special about the lion says. Or the lion sleeping or anything else. Because in the jungle, the lion sleeps tonight. Yeah. You do recognize that, yeah. But we won't sing that. Please. So we have 2 mnemonics for this chapter. The first one was, which, according to Valerie, might be something from Michael Jackson's iconic song. Wasn't that you that put that? No? Oh, it was Hannah. Okay. I thought that one was pretty good. I didn't put that on the test. It is a question I used, but I didn't use that. So what did BAAD stand for? And it also had nothing to do with sheep. Okay. And that refers to what particles? Yes. So I'm going to put H plus because that's what most of our things said. Proton is the same thing. It's just different name. And then we have our second one that is Leo the Lion Says GER. And what does that have to do with? That has to do with electrons. So lose electrons, oxidation. Gain electrons, reduction. Versus bases, absorb. Okay, A and D. My brain just went blank on me. Except, yes. Not absorb, except. It means the same. It would have been good. And acids donate. I was thinking defer, and I knew that wasn't right. And yeah, obviously. Do a better job than me of remembering that because that is one that could be on your next quiz or test. So 2 different types of things. One's dealing with electron exchange. One's dealing with proton exchange. Here's what happens if you put sodium and chloride together. Chloride is a good oxidizer. Sodium is a reducing agent. So, I think it's when we put those together, the sodium, what happened to sodium? in that reaction? Was it oxidized or reduced?
Reduced.
It was.
Okay, we had a strong reduced. Our rule was gain electrons means reduce. Did it gain electrons? No, it lost electrons because it became positive. So that was reduced. And the chlorine gained electrons, so that was oxidized. So the sodium was the oxidizing agent because it oxidized the chlorine. Or I said that backwards. Shoot. Sodium was reduced, the chlorine was oxidized. I said it backward. Outcomes, right? I've never seen this, sadly, but if you take elemental sodium, it will react very strongly with oxygen, such as in water. So if you take elemental sodium and you put it in water, it has a very rapid oxidation. Here's what a rapid oxidation looks like. It goes boom. So when I was in high school, when I was like not there, my physics/chemistry teacher took my other buddies down to the beach, and from the bluff, they tossed a baseball-sized chunk of sodium into the ocean. And then they watched the big as it explodes in the ocean. I didn't get to see that. I feel very, very bad about that. So you don't see elemental sodium because it's not stable. Just the water in the atmosphere might be enough to start a fire. And so for storing it, they store it in something like an oil or something so that it won't be oxidized and start a fire. Okay. I think it's pretty clear by now. We've talked about the electronegativity, how strongly something wants electrons. Things over here really want electrons, so they tend to gain electrons. Hence, they are more likely to be gain electrons reduced. The ones over here, they're happy to have a complete shell plus one. So they're happy to give off that plus one electron. So they're happy to be oxidized. These are not the same words, but they're the same outcomes. So oxidation, lose electrons. That's what we learned. If you put an is in there, it made sense. That is what we learned. This is the standard Leo. Lose electrons, oxidation. But here we have another option. If you gain an oxygen, you're oxidized. It doesn't have to be an oxygen. You could gain a chlorine or a fluorine and be oxidized as well. But we usually think of oxygen here as our primary oxidizer. So it's oxidized if it gains an oxygen or if it loses a hydrogen. So those are three different things that are oxidizing reactions. And then we have the reducing reactions that are just the mirrors of those. So we have the mirror of lose electrons was gain electrons, the GER. And instead of gaining oxygen, we lose oxygen. Instead of losing hydrogen, we gain hydrogen. So now we actually see there is a relationship between our acids and our bases and reduction and oxidation. Because an acid donates a proton. So that means the acid loses a proton. Here we have oxidation loses a hydrogen. So those are in the same ballpark. It's losing a hydrogen. Now, let's just move on from that. What element? Oh, yeah, I started it. It's just been so long that this fell asleep. No, I didn't start it. Start sesame. Okay, now you can answer. I did. Yeah, you can answer now. What element within the reactants is oxidized in the following equation? And what element is reduced? Finally getting answers. I was worried.
myself. Yeah.
Okay, Eric and Carmen. There's no trick question here. Do you guys have your clickers?
Yeah, I do.
Okay. Just want to make sure I'm not waiting for no good reason. It's the only clicker question, so if you don't get in, you lose your points for today. Okay, everybody's answered. We had 7 that said iodine is oxidized, bromine is reduced, and 11 that said it was the other way around. So talk to your neighbors about how you make that decision about which one got oxidized and which one got. I see that it looks fine in one place, it's the other. There is plain information. Talk about it amongst yourselves.
The I2
Well, I was fairly sure that it would be until I convinced myself that it was probably.
That's why I said ER credit.
Yeah, the other way around. No,
So I can work. So I 2 plus 1, 2
Okay, let us answer a second time. It is open now for you to answer a second time. That's a good thing to say. Did it make so much more sense now? Okay, good job. We all answered. And this time around, all but one person said, I see that my lines are off here, but that's okay. This time it was 117. Yeah, 0. Those of you who are using cell phones, if it shows you the question, it had the answers in a different order.
It did.
Yeah.
It had like A as the equation.
Yeah. I that's why I was noticing, wow, that's formatted wrong. And then I noticed, wow, it's listed as A here where it's not supposed to be. Okay, so I'm going to go with this as it is and go to Carmen and ask her to explain herself.
So if you look at so what I chose B, and because if you look at the iodine in the first one,
Okay.
then it's like positive, and then it becomes a little negative sign, and then same with like it was opposite.
Okay, so it went from 0 charge to being negative. And so what did it do? Did it gain electrons or lose them? If it becomes negative, it gains an electron. So that gained electron, and what goes with gained electron? Grrr. And so because the iodine gained an electron, then it had to be the one that was reduced. So you answered correctly. So that was one of the 2 ways of analyzing it, right? And because of the other answers, you really did want to look at the bromine to make sure that you understood correctly. So if we look at the bromine went from a minus sign to a 0. So going from minus to 0, you've lost a negative. Remember, electrons are negative charge, which is what was confusing there. So if it's lost an electron, then it's oxidized. And so we have the bromine was oxidized. So how is this useful to you and me? Do you ever wonder that in your science classes? Every day, Brittany Renee says, how is this useful to me? Well, one way that we can use these redox reactions is for heating, for producing energy. The two that are listed here are batteries and fuel cells. What's the difference in a battery and a fuel cell? In a fuel cell, you have a chemical reaction like in a battery, but you're actually putting stuff in as well. So let's look at how a battery works. Here we have something that has iron on one side, chlorine in the other, and you're going to have a chemical reaction. You have iron that gets etched away, and what happens to the iron? It goes from neutral to positive. So is that okay? It's losing electrons, so that means it's oxidized. What do we call it when we oxidize iron? Rust. Yeah, rust. So basically it's rusting. And so it's losing electrons. So the electrons stay on that nail. Well, now the nail has excess electrons. So that's a source of electrons. Now, if we look at the copper over here is in chlorine, and we have copper that's in the water attaches. Notice the arrow is the copper attaching and becoming neutral. So if we have copper 2+ and it becomes neutral, what happened in terms of electrons? It gained 2 electrons. So gain electron reduction. So we had oxidation over here, reduction over here, and the result is that this side here is electron poor. This one's electron rich, so electrons flow from the place that has extra electrons to the place that is missing electrons. And that's the basis of how a battery works. Now this here, I have to point out, would be called a cell. A battery is a battery of cells. That has more than one cell connected together.
So that light would turn on?
That light would turn on if it can run on the small amount of current this produces. Right? Because it's not going to be a huge amount of current. It's not like you're going to have arcing or something, right? So you have to have the right kind of light for it to do anything.
So
but
if it would turn on,
a flashlight light bulb would turn on.
Will the water level start to go down?
No, because you're not moving anything. In this situation, you're not actually moving anything except for electrons. And the mass of electrons is virtually nil. So now if you produce gases, then of course you would have a change. So that's an example of a simple battery. And so where do you see a simple battery like this? Well, you need an acid in there to make it happen. So oftentimes we'll just take a lemon and you jam a nail into one side of the lemon and you jam a penny into the other side of the lemon. You connect a wire going from those to your light bulb and it turns it on if it's like a flashlight light bulb. Yeah. And part of the reason you put them both in the same lemon is because then the electrons that go from one to the other can flow back over, so you have a cycling of the electrons.
We should do that in the lab.
It's more of a grade school lab. That's the kind of thing that you should do when you're a teacher.
We'll get A's. I feel like you should try it with a grade mate.
My son did it in 6th grade.
Maybe I'd like to.
Or maybe you'd like to teach 6th grade to do it, right?
Exactly.
I mean, it is a good thing to do. It's a good thing to know how to do it. Yeah, that's all it takes. Here is putting a salt bridge, something to allow the transport of charge to make it so it actually works. Because here you notice the light didn't turn on because you didn't have the flowing of electrons going through. Here you have the flowing of charge in between these two things for it to work. Most of the cells we use, notice this, better than my own physics textbook, calls it a cell. A single cell. When you have a AA, it's not a battery, it's a cell. This is a battery. This is a 9-volt battery. Each of these cells makes somewhere nominally around 1 volt, 1 to 1.5. It depends on how it's made. And so to get 9 volts, you have to put multiple cells in there. So this is a traditional creation of a dry cell where you have the graphite rod in the center. That's the thing that's going to stick up. And then you have a zinc cup around the outside, and that's going to be connected to this. And then in between, you have a paste, it's dry rather than liquid, of materials that are going to undergo the reduction and oxidation at the different metals. Positive electron, positive cat. Okay, so just in case it comes up, and is negative. So the negative electrode's probably the next slide. I forgot to remove it. The anode is the negative electrode. The textbook gives me slides, and I go through and edit them, and it has like 5 slides I usually combine into one. But here I forgot to, see? So negative electrode is the anode, positive is the cathode. So an versus cat. Moving forward, rechargeable batteries are not the same as other batteries. What makes a battery rechargeable is that if you force current to go the wrong direction, it will actually reverse the chemical reaction, make it work the opposite direction. So when you're charging a rechargeable battery, the reaction is working in the opposite direction, so it's rebuilding the chemical supply so that it can then work again. If you don't have a rechargeable battery, it won't actually run backward. And so you try to do that, and it just gets hot and then goes pop, like her gum. And so that's why you want to make sure you don't try to recharge a non-rechargeable battery. It's not really safe. We have a couple things here. I think that's nickel metal halide. Might be hydride. And then we have lithium. Usually we call them lithium ion atom or batteries or lion, right. Then there's fuel cells. Okay, so I don't have any discussion about that, but what's a fuel cell? I said it's like a battery, except you put stuff in and out. So here's an example of a fuel cell. You have 2 things. What did we say the one that's positive is called? It says it there, I know, but just a reminder.
Cathode.
Cathode, right? The one that's positive is cathode, the one that's negative is the anode. And you put in hydrogen here on the anode side so that it will undergo a reaction here. 2 hydrogens plus 4 hydroxide produces 4 waters. So it's producing water. You put in hydrogen, water comes out. Not a bad thing to have water come out. I see water coming out of my tailpipe all the time because when you're burning gasoline, you're also producing water. On the other side, you put in O2 and water, and what comes out? O2 and water. Here's the reaction there, where you have O2 plus water gives you 4OH minus, but that OH minus is going across rather than coming out. So the OH minus is what's completing the circuit, so charge is going in a loop. But this has 2 different reactions, so you have to have different materials on the 2 different sides. And you put hydrogen in on one side, and you get out water, put in O2 and water on the other side. You get out the same thing, but you facilitate the OH going across. So this fuel cell, you put in your fuel, and it does the chemical reaction. Whereas a battery, you're not changing anything in there. You have a sealed battery in your car. Now, when I was young, you didn't have a sealed battery. You'd have to put in more acid. But they have improved the process. What's electrolysis?
Using electrical energy to produce chemical change.
Well, that's true. Let's say my sister's brother-in-law, I think he does electrolysis for hair removal. I believe that's what they call it, and you're basically putting little arcs in there and killing the hair follicles. Electrolysis, though, in chemistry class is when you're using electricity to separate a molecule. And so you can do electrolysis and things like you can put 2 electrodes in water and have one bubble up oxygen gas and one bubble up hydrogen gas, where you are you're separating the molecules, and the hydrogen comes off on one and the oxygen comes off on another. And that's not the one that they're showing here. But you see here you have the aluminum fluorine becomes aluminum and fluorine, or aluminum fluoride. That's electrolysis. We're so much almost out of time. 3 minutes left. Corrosion and combustion. What are corrosion and combustion both examples of? I've talked about both of them today. Oxidation. So corrosion, that's going to be things like rusting, at least I believe it is. Yep. They coat metals with zinc, like most of your nails are zinc coated, because the zinc will be oxidized instead of letting the iron be oxidized. And so instead of rusting the iron, you have the zinc that gets oxidized and looks nasty but doesn't rust. And combustion, here is burning a nice, safe, and sane fuel, methane gas. Methane is a single carbon with 4 hydrogens. So that's CH4 plus, and here they showed 2O2, so I'm going to assume that they showed a picture that's balanced. When we put these two together, it undergoes a chemical reaction to produce CO2 plus 2H2O. Now, is that balanced? Yay or nay? Okay. How do you determine if it's balanced or not? Chemical stuff. Well, we have 1 carbon, the blackest carbon, 1 carbon. That's balanced, right? 1 to 1. We have 4 hydrogens here. 2 times 2 is 4 hydrogens there. We have 4 oxygens here. 2 plus 2 is 4 oxygens there. It's balanced. Right? Whenever you do these, you want to make sure the equation is balanced. You never know when the book's just going to get lazy and just show one example of each molecule instead of the right number. When this occurs, the binding energy between the molecules becomes stronger. That is, they're more tightly bound together. The CO2 and the water are more tightly bound together than CH4 and O2. Because they're more tightly bound together, you drop to a lower potential energy state. Energy can't be created or destroyed. It has to be released. And when that energy is released, it makes things fly faster, the molecules in the air. And if they move faster, what do we call that? A higher temperature. And so this reaction results in a higher temperature because the energy released goes into making gases move faster, higher temperature. And notice you have this water as a major constituent of the burning, of the oxidation of the fuel. Okay.